Welcome to This Explainer. Today, we're going way, way back to the ultimate beginning. I want you to think of the early universe not just as some abstract, chaotic explosion, but as a highly structured cosmic kitchen. And this kitchen? It had an unimaginably strict, non-negotiable timer. We're diving into Big Bang nucleosynthesis, specifically looking at the absolutely fascinating events that went down in the very first 3 minutes of existence.
Now, to really wrap our heads around the massive, cosmic scale of the Big Bang, we need to bring it right down to physical reality. Literally, look at your hands for a second. Think about the solid matter making up your own body. Where did the atoms inside you actually come from? To answer that, we have to understand exactly how the very first atoms in the universe were forged.
Okay, let's dive into this master timeline. Think of it as our roadmap. At 0 seconds, we have the Big Bang. At about the 1 second mark, protons and neutrons are firmly set. Fast forward to 3 minutes, and fusion finally begins. Then, by roughly 20 minutes, fusion completely ends. You see, the expanding, cooling universe dictated exactly which nuclear reactions were even possible at each of these ticks of the clock.
Which brings us to Section 1. The cosmic kitchen opens.
So picture that very first second. The energy was so incredibly intense that matter, at least as we know it, didn't even exist yet. It was essentially just a swirling soup of fundamental particles. I mean, sure, protons and neutrons did form, but the universe was far too hot and way too dense. Everything was zipping around way too fast for anything to actually stick together. If any atomic nucleus somehow managed to form, boom, the ambient energy instantly blasted it right back apart. Moving to Section 2, freezing the first second. Right around that 1 second mark, a really crucial balance is struck. And it gives us this ratio, 1 to 7. That's 1 neutron for every 7 protons. Why that specific number? Well, neutrons are actually slightly heavier than protons. So as things cooled down, nature simply ended up making fewer of them. Before this point, reactions were constantly swapping protons into neutrons and vice versa. But as the universe rapidly expanded, those swapping reactions became too slow. They just stopped. The ratio completely froze at exactly 1 neutron for every 7 protons. And this single number quietly sets the final recipe of the whole universe. It's absolutely crucial. Because that 1 to 7 ratio is permanently locked in, it mathematically dictates the chemical fate of literally everything that follows. The universe now has its raw ingredients measured out exactly, and there's absolutely no changing the mix.
Let's look at Section 3, the Deuterium Bottleneck hurdle.
Here's the thing. Building any element has to start with deuterium, which is just 1 proton bound to 1 neutron. But we hit a major dramatic hurdle here. Deuterium is incredibly fragile. Before that 3-minute mark, it's just too hot. Extremely energetic photons smash the deuterium apart literally as fast as it forms. So element building absolutely cannot get started. It's a massive cosmic bottleneck. But then, right after about 3 minutes, the universe expands and cooled enough, down to a brisk 1 billion Kelvin, for the deuterium to actually survive. Suddenly, the bottleneck clears, and fusion races ahead.
Which brings us to Section 4, baking the universal recipe.
Now, what's really interesting about this next phase is that once that fragile deuterium survives, fusion kicks into high gear. The cosmic assembly line moves incredibly fast. We go from a proton and a neutron to deuterium, which rapidly fuses into helium-3 and then almost instantly into helium-4. It's a rapid, unstoppable sequential chain reaction. And because helium-4 is so exceptionally stable, almost every single available neutron gets permanently locked inside a helium-4 nucleus. All those protons that couldn't find a partner on the cosmic dance floor, they were left all alone, simply remaining as single hydrogen atoms.
This furiously fast process left us with the ultimate cosmic recipe, cooked up by the Big Bang. Because of that rigid 1 to 7 frozen ratio of neutrons to protons we talked about earlier, the literal math dictates that we end up with roughly 75% hydrogen by mass and about 25% helium, which, remember, contains almost all of those trapped neutrons. Everything else? Just tiny, less than 1% traces of things like leftover deuterium, helium-3, and lithium-7. The whole universe's base recipe was perfectly baked in just a few minutes.
But then, everything stops. Section 5, the sudden mass gap.
Nature suddenly hit a hard physical wall. To build heavier elements, you need to add particles to helium, which has a mass of 4. But here's the catch. There is absolutely no stable nucleus in nature at mass number 5 or mass number 8. If you try to fuse a stable helium-4 and a single proton, you get a mass of 5, and it instantly falls apart. Try to smash 2 helium-4s together, you get a mass of 8, and again it just falls apart. With the universe rapidly expanding, cooling, and thinning out, fusion simply could not climb past lithium. The gap was just too wide. So, within about 20 minutes, the timer went off. The cosmic kitchen abruptly and permanently shut down its operations.
This leads us to Section 6, Echoes of the Big Bang. Now, you might be wondering, how do we confidently know these incredibly specific reactions actually happened 13 billion years ago? Well, because Big Bang nucleosynthesis makes precise predictions that we can actually test today with our telescopes. We have 3 main pillars of evidence here. First, the helium abundance. That 24 to 25% helium we just calculated, that perfectly matches the amount of helium we physically measure across the entire observable universe today. Second, the light element traces. The observed amounts of leftover deuterium and lithium in the oldest stars fit our calculations beautifully. And third, the cosmic microwave background radiation. This is the literal fading afterglow that confirms the early universe was exactly the hot, dense environment required for this whole process. So the physical, observable reality absolutely proves the math.
So, here is our final takeaway. The Big Bang's 20-minute cosmic kitchen successfully cooked up the foundational gases of the universe. It gave us all the fuel, the hydrogen and the helium that powers the stars. But because of that insurmountable mass gap, it completely failed to make the bricks. It made no carbon, it made no oxygen, it made no iron.
Which brings us right back to you. As we said at the start, your body is fundamentally full of carbon, oxygen, and iron. But the Big Bang made absolutely none of it. So, where did it come from? If the universe's cosmic kitchen completely shut down after just 20 minutes, how did the heavy elements inside you actually get forged? Well, that is a spectacular mystery for you to ponder. Thanks for joining me for this explainer, and keep asking those big questions.